Welcome everyone back to Rocks for Jocks. Today I'm really excited to speak with someone I looked up to in college, Danielle LeBlanc. Danielle was a master's student while I was in undergraduate at Boston College. Since then, Danielle has gone on to finish her PhD and is now working as a postdoctoral researcher at the Woods Hole Oceanographic Institution, which is one of our country's biggest and best research programs. I've been reading up on some of Danielle's research, including her work analyzing ocean sediment components, to learn about what our climate and ice sheets have been up to in the past. A quick note for listeners, which I'm recording after my conversation with Danielle is over. There are a few times during this episode where I mentioned the word soil. I would like to note that this was a mistake, and what I meant to talk about was ocean sediment. I'm not an expert on the subject, so there's a fair chance I get corrected again, but here is the difference according to Oxford Academic, which seems fairly reputable. Oxford Academic says that soil is a mix of organic components and broken down rock. In other words, soil is stuff on land. On the other hand, sediments are when that broken rock gets transferred somewhere else, like the bottom of the ocean. Today's guest, Danielle, has done her research on ocean sediments, not soil. There are also a few times where we reference someone named Jeremy. This refers to Professor Jeremy Shakin, who is my undergraduate thesis advisor, and at the same time, he's also Danielle's graduate thesis advisor. So we both individually spent a lot of time with him and appreciate all his hard work, which I hope comes through in this conversation. Thanks everyone for listening. If you like this episode, please give it a like, give it a subscribe, give it a 5-star review on Spotify and Apple Podcasts. That helps the show grow and reach more listeners, and I appreciate it more than you will ever know. All right, let's jump into things. Starting things off, do you want to maybe tell me a little bit about your undergrad, what you maybe started with studying, and how you got into earth and environmental sciences stuff?
Yeah, sure, of course. And thanks again for having me on the podcast. I'm excited to be here and chat with you and catch up a little bit too, since it's been a few years since we were both at BC and the Earth Sciences Department. Before moving to Boston and coming to BC, I was in Louisiana. I lived there all of my life and went to undergrad at Louisiana State University and studied petroleum engineering. So completely different than what I'm doing now. I didn't really know what I wanted to do with my life and career when I entered undergrad, but I had family that worked in oil and gas and they spoke very highly of it and said it paid the bills. So I kind of figured, why not?
Cool. And then how did you jump from oil and gas then to your master's degree? Yeah, can you maybe tell me a little bit about that transition?
Yeah, absolutely. So I have always, since I was a kid, had this fascination with earth sciences. I didn't quite know how to bottle that up and use it in a career. So it took a lot of dabbling and exploring to figure out what that would look like. Actually, when I was finishing undergrad, I was offered a job in oil and gas that then was rescinded during the oil downturn in 2015. And ultimately, that was such a blessing in disguise. Though at the time, you're thinking, oh no, I don't have a job when I finish undergrad. What am I going to do? But it really led me to explore a lot of other interests that I have, including the earth and environmental sciences. I worked as an environmental engineer for a year, as well as many other odd jobs on the side. And during that kind of 2-year period, I volunteered in a lab at Louisiana State University looking at ocean sediment and helping sieve some of that mud for research being done there in a paleoclimate lab. And when I was doing it and reading the papers about what I was doing, I was just absolutely blown away and realizing that this was even a field. I had never really heard of it before. So I really got the bug when I was doing that kind of volunteer research on the side. And when I came across Jeremy's work, it was just like a no-brainer. I was like, this would be great. If I get into this program, like this is it.
Yeah, he's great, right? Super easy to work with. Great mentor, teacher to have around, I think.
Absolutely wonderful. He's just been such a transformative advisor and mentor through my academic journey so far.
Perfect. And then one thing I wanted to clarify, you mentioned the word paleoclimate. That obviously comes up a lot in your work. Could you maybe give like a 30-second breakdown on what that means?
Yeah, absolutely. The way I like to say it, like even just to myself, is I like paleoclimate really is just climate history. We want to know what Earth's climate was doing in the past. And the way that we reconstruct things like paleoclimate, climate history is we use different Earth archives that give us kind of layers like a history book. We can think of like ice cores, layers of snow accumulated, each page of the history book that tells you something about Earth's past.
Perfect. Yeah, that's exactly what I was looking for. Thank you. I think I saw maybe on LinkedIn somewhere that you had worked at one point with some of the cores from the International Ocean Drilling Program. Is that right?
Yeah, yeah. No, I most of my PhD, actually, my entire PhD hinged on the IODP sediments that have been drilled from mostly the North Atlantic, but that is the integral part of my research journey so far.
Cool. When I was finishing up my undergrad and looking at graduate schools, I went for a tour down to Texas A&M for their master's program, and they ran us through the warehouse of, I guess they're really heavily associated with the International Ocean Drilling Program. So they walked us through the warehouse with a bunch of the cores, and it was astonishing. There was like tens of thousands of cores, both soil and ice, stacked up in huge refrigerated rooms. It felt like just giant piles of scientific data waiting to be explored. Just really impressed with that, I guess.
Yeah, I am not sure if we were in the same warehouse, or I'm sure Texas A&M has multiple warehouses of cool geologic data waiting to be studied. But yeah, I was actually down at Texas A&M a couple of years ago as part of I was a scientist in IODP Expedition 395 and 395C in a shore-based capacity. And so I went down there for 3 weeks and we were taken into this like big freezer room and just like yeah, stacks of ocean mud like in tubes that they had like taken out of like the sediment on the ocean floor. And yeah, it was just there. And I was there to actually help describe those sediments for like record keeping purposes so people would
Mm.
know where to go and if they were looking to study like some specific like I don't know layer of like sand or something. That it really is just an incredible facility down there. And I felt like very special experience to be down there and see it.
Yeah. For the listeners, the reason it was so surprising is because I had seen these soil cores before up in Boston, but only like one of them at a time. And it would be, a 3 foot or 1 meter chunk, whatever it was. And then all of a sudden I walked into a room of tens of thousands of them, from all over the ocean, all over different time periods. Everything, all the data you could want was probably stacked up in there, just waiting to be dug into.
Yeah, no, it was really I remember when we went and got a tour of the facility, I immediately got my phone out. I was like, "I have to take a video of this just so I can, like, look back and remember how crazy this is." Because it just yeah, it was a library of ocean sediment cores that you could then go back and yeah, get the intention right is to save them, keep them cold, and preserve them, and then scoop out these chunks that you can actually like scientists will put in requests and you can have them shipped to you whenever you would like to do some sort of analysis on the material. So that's the idea of like this big refrigerator of sediment there being like waiting to be used.
Cool. Yeah. Danielle, do you want to maybe give, if you can, do you want me to give like a 30-second description of kind of what isotope geochemistry is? I think you're probably going to have a lot better shot at doing it well than I would.
Yeah, I'll do my best. So yeah, isotope geochemistry, I guess the way to think of it is that everything around us is made of atoms. They're the building blocks of things here. And atoms that have a core, a nucleus, which is composed of even smaller particles like neutrons and protons. And so, like isotopes are a type of atom with the same number of protons but different number of neutrons. And so, isotope geochemistry is when we actually study the changes in the abundances of different isotopes found in things like rocks or other earth materials, which is just an absolutely mind-blowing concept. But that is kind of the general idea behind that sort of like I'd say subfield of earth sciences is using like the composition of different earth materials in order to infer some more information about those things. Is that kind of what you're thinking?
Yeah, that was a really great way of putting it. The ratios between the different isotopes that we look at reveal something about what's going on around the soil at that time. So, for example, when I was reading through some of your work that you'd send me, by looking at some of the ratios between isotopes, you're able to tell kind of how much sunlight
the soil was getting at different time periods, kind of whether or not it was covered by ice sheets for certain time periods, how long it was covered for, that kind of thing. Is that right?
Yeah, I guess I was giving like the big picture of what the field is, but yeah, in terms of applications, oh my gosh, there's so many ways. I think ratios of isotopes is certainly a helpful direction. You can use isotopes to tell us anything from like the age of a rock to how long they were maybe covered by an ice sheet. And so, yeah, part of my work has focused on looking at in the sand grains, so like the quartz sand that's found in some of these ocean sediment, ocean mud cores. And we look at the ratio of some of these isotopes and infer things like how long they were on land, how long they were buried by an ice sheet. And I think what you're also kind of getting to is like the sun exposure. The way I kind of think of it is it's not so much the sun, but it's the cosmic flux. So like the subatomic particles coming in from even further out, just out of outer space coming in and
Oh,
bombarding
really?
Earth's surface. And that's where like the production would come from in these materials. But an easy way to like wrap my mind around it, and I think a lot of people use this analogy in the field, is actually rocks on Earth's surface kind of getting like a sunburn, even though it's not like the sun's rays that are actually doing this, but it is like when you see this, when the ground sees the sky, that is when you will have like the production of these isotopes in the rocks, and the longer they're exposed, the higher that concentration is going to get. And then you put an ice sheet on top, and that can actually block the production. Or I think you can think of the ice sheet as a sun repellent, a sunblock, or a t-shirt that you might wear out on a hot day.
Oh, that's so cool. I didn't realize that it was the cosmic flux was coming from other sources. I just assumed it was our sun.
Yeah, so it's I think that is a whole another philosophical question of where it is that cosmic flux is coming from, and like what modulates that, how much is coming in. I think people tend to say like far, far out in space coming in, and that is really outside the area of my expertise. But yeah, the idea is that there's like these high energy particles coming in through Earth's atmosphere and like bumping into the ground at high speeds, and that creates a, a reaction that produces what are known as cosmogenic nuclides.
Okay, cool. And you mentioned that the work you were doing was coming out of the mineral quartz. Can you describe kind of how you separate out the quartz from some of the soil cores that you get?
Yeah. So the idea, kind of like we were talking about, is you have these ocean mud cores that are being stored at places like Texas A&M. We order, let's say, I want to study this interval. You get a scoop of that material. It is shipped to me in Boston, and then you have like a little like nugget of mud that I then kind of wet with water and shake up, and then pour through a sieve. So you think like a pasta colander, where you just like drain out the water and you have the pasta left. Well, my pasta is these rock fragments, these sand grains that are left in the mud. And that's a mixture of different minerals, right? You have quartz, you have hornblends, you have other things, maybe like some shells too that are in the coarse fraction. It's a series of steps where dissolve all the shells in there with things like hydrochloric acid. And then progressively, the acids get scarier and scarier as you go along the protocol. Because when you think about it, to dissolve something like a rock, you need something pretty potent. In this case, we use hydrofluoric acid and nitric acid and give the rocks a bath. And then you're eventually left with pure quartz sand. And that's what we want. So that's about what the process is like.
Cool, cool. And then do you end up running it through a TIMS machine or a mass spectrometer or something like that at some point as well?
So I don't, but someone does later on down the line. That part of the protocol was where we just get the quartz sand out, but then there's a series of steps where then that quartz is actually dissolved into a solution and put through a series of column chemistry, which are like really fancy chemically altered filters to get out the atoms that we actually want to analyze. And then
Mhm.
that is actually extracted, and then it takes like a week or two to actually do that process for like 10 samples, and then it's packed into a cathode and shipped off to be analyzed on one of the machines that you're kind of talking about. I have not done that process. That is done by our absolutely wonderful lab manager at University of Vermont, Lee Corbett. And she tends to take those trips out and do those analyses for us, which is we're very thankful for.
Cool. Okay, great. Yeah, and so I'd love to jump into the paper you sent me if that's all right.
Yeah, so the paper focused on what is known as the Laurentide Ice Sheet, which is the ice sheet that used to overlie Canada, like eastern Canada, and even as far down as Boston thousands of years ago. And throughout the Pleistocene, which is about last 2.5 million years, ice sheets would come and go and ebb and flow across the landscape. And the idea that's taught in paleoclimate courses and across the community is that when it's cold during what's known as a glacial period, the ice gets big, and then they shrink down when it's warm during what is known as an interglacial period. But I guess what's not known too well is how much ice sheets shrink in size during these warm periods. Like, is it completely gone and there's no ice anywhere in the landscape, or does it shrink down just a little bit along the edges so that you aren't breaking off icebergs into the ocean? And this is kind of an open question. And what my results seem to suggest is that the Laurentide was likely sticking around during some of these warm interglacial periods in Canada, which was really surprising and something that I think more and more folks are starting to look into and test this hypothesis from different angles, because we had really thought that way before, or I hadn't thought that way before. So it was cool for like flipping the idea around in my head for a little while.
So I guess kind of in that vein, how have you found the results being received by others?
I think it's prompted a lot of fun conversations. And I think, if anything, the most fun conversations have been people actually coming and saying, wow, this is really interesting. I actually have found something that suggests this as well. Or saying, yeah, this is something we should really look into. I'd say, generally speaking, it's been positive, fun conversations about people saying, like, I want to go look into this more, or I, yeah, was actually going to put this in my paper, or something along those lines, that like my results suggested something similar. So yeah, I feel very lucky that everyone has been very, very positive about it. But yeah, I think it's also important when finding something like this to preface it by saying, like, we're looking at like one data set. There's many other data sets that need to be looked into. So it is, right, like something to be tested by science moving forward. But everyone, yeah, has been very positive about it.
Perfect. That's so great to hear. I'm so happy that it's working out well. Was there anything surprising that you found during that project? Anything that kind of popped out to you out of left field that you had to find a way to square with either data from other studies or data that you had already started with in the first couple of months? Yeah, anything like that might be interesting.
Anything surprising? Data, if you're lucky, all the data comes in at once. But if you're a scientist doing actual science, most of the time it's not all at once and it trickles in little by little. And then you get excited and you start looking at the preliminary data and coming up with potential conclusions and hypotheses. And the way it worked is we started off with a little bit of data and we were thinking, this is our conclusion. And then we get more data, and it turned out to be the ratio data in this case. And we're like, wait, that doesn't go with the hypothesis we thought before. So yeah, it was a lot of just kind of evolving the interpretation as we got more data along the way. But I think that's kind of like the exciting part of science, right? Is you just adjust as you learn more information. So I think it was just kind of the normal about us, surprise that goes along with doing science.
Did you end up changing your research questions at all during the process? Like, did you start with a certain null hypothesis, for example, and then decide to switch to something else or add something else on top of it halfway through? Anything like that?
Yes, I think this project was actually pretty it was pretty exploratory, where this is this new method that our former advisor Jeremy and his collaborator Paul Bierman are kind of spearheading and getting applied into different sites. Would say, going into it, we wanted to target these specific intervals that were pretty mysterious in the ocean sediment layer. There are these layers of sand that extend across the North Atlantic that have been linked to massive ice sheet discharge events that happened during the last glacial period thousands of years ago. So we wanted to learn more about ice sheet dynamics, like actually connected to these events and how much like the ice sheet was gone or around, it turned out being this much bigger story than we had just targeted one small intervalent balloon into. Wow, in order to explain this, we actually need to think about the entire time that ice sheets were coming and going over the past 2.5 million years. We can't just focus on the last 60,000 or 100,000 years from when the samples were from. So I think in that sense, yeah, there was an adjustment of time scale where we went and targeted
Mm.
several thousand years and said we're going to look at samples from this interval. But then in order to explain the data, we actually had to do some simple modeling that extended deeper in time in order to explain the accumulation, like concentrations, the decay that happened. It could only be explained by something that happened prior to the interval that we were looking at, if that makes sense.
Yeah, absolutely. That's a pretty big change. I think that's a good one to think about. I know this is only one of probably a handful of projects that you've done during your dissertation. Any other big findings from some of the others that you want to talk about?
So I guess those are still being written up. They're in my dissertation, of course, but I'll probably keep those under wraps until they're formally out in the open. I am focusing on other proxies, other like ways of looking at the ocean mud. So I looked at some nitrogen isotopes and shells known as foraminifera, and those are found in the ocean sediment as well. So I'm kind of looking at like the nutrient dynamics in the North Atlantic over the last 2.5 million years during the Pleistocene, the source of rocks that, so basically when I'm talking about these rocks in ocean mud, it's known as ice-rafted debris, and or IRD is what everyone in paleoclimate likes to call it. And what happens is ice rafted debris is sourced from underneath an ice sheet where it actually like picked up and kind of stuck to the bottom or within the ice. And then when an ice sheet flows towards the edges and meets the ocean, it breaks off or calves off icebergs. And so within those icebergs, it actually has sediment and rocks that were picked up earlier on, stuck in the iceberg. And as the iceberg kind of floats around, that stuff melts out with as the ice melts, and that is deposited onto the ocean floor. So I have this fascination with ice rafted debris and IRD, and that was what the first chapter that we talked about is focused on, as well as another chapter which is looking at the source of these rocks. So were the icebergs coming from North America? Are they coming from Greenland? Are they coming from Europe? We can look at the ages of those rock fragments and kind of match them like puzzle pieces to the different rocks on land, like the continental rocks, and say, oh, if we have a 400 million year old grain of sand, maybe it came from this area of the continent. And so that was another kind of component is matching the source of those rocks to say, if the iceberg came from North America, then there must have been an ice sheet there that made the iceberg.
That's awesome. That's so cool. Yeah, I was curious about the ice rafted debris. If you could explain maybe like the reason why you choose to look at ice rafted debris when that stuff's all moving around all the time. Ice rafted debris moved around millions of years ago or hundreds of thousands of years ago. What the purposes of looking at ice rafted debris versus soil that sits in any one spot, at least from our perspective. Like, why would you bother getting soil from 10 different places that's now at the bottom of the Atlantic Ocean instead of soil that's just sitting on land?
Yeah, so what's special about ice rafted debris is, and the way that you actually identify it, if you're looking at a core of mud in the middle of the ocean, is it's much coarser. Like the grains are much larger than like the surrounding mud because it like you can't get those coarse grains from anywhere else. Like you can get mud, like very fine grain stuff kind of floating around in the water, being pushed around by the currents. But the larger the grains get, the water can't carry that material very far. So the way you get something coarse into the middle of the ocean is you got to have icebergs that are helping, like a very powerful source to kind of convey it from land to sea. And I guess the reason you want to get it from the middle of the ocean far away from the continent is don't you want to make sure it's not just from like turbidity current or like some other like disruption that might be happening closer to shore. So the further you get out, the more likely you can be confident that you're looking at ice rafted debris. And so yeah, if you were to go get a scoop of sand from a river, there are other powerful agents that can bring those coarse grain materials to where you're sampling. So you can probably not be so sure if it's a river or if it was like left by an ice sheet that was kind of bulldozing stuff around thousands of years ago, or if it was a real bulldozer. Honestly, if you were going to look at something today. So does that answer your question? Kind of like how you would be a little bit more confident?
Yeah. No, that's perfect. Exactly what I was looking for. Just kind of explaining what the reasoning was. And then something else I noticed as well, there was a sentence somewhere in here that said something along the lines of even after the soil is deposited, a lot of it gets mixed together. So it sometimes is a little tricky to tell exactly which year the soil is from. I was wondering if you could maybe explain some of the strategies that you guys use to deal with that and kind of how you start to approach dealing with that issue.
I think with this paper, we were quite lucky that we studied very well studied layers in the North Atlantic, Heinrich layers. And those are the discharge events I was referring to before. And they are identified as these like layers of ice rafted debris and across the North Atlantic. And like these, like, if you're looking at like a sediment core, it's like a band, and there were quite a few of them. And they were identified decades ago and really have been a fascination for the paleoclimate community for the past few decades, and still very mysterious in a lot of ways that I won't get into today because it's very niche. But what makes them extra helpful with this kind of work is that so many people have done a nice job of building up the age constraints on these events. And there's still like an element of like mystery there because like we can only be so precise when we're looking at layers of ocean mud. But that has not been my work. This work was highly dependent on decades of research that came before us that went to the specific sites that we were at and said, we are going to go date these layers and we're going to provide some constraints around the timing of when these big discharge events from the ice sheet took place. So not my work, but it was dependent on lots of age constraints that came from other people.
Cool. Cool. That's awesome. And then the last question I want to hear about research stuff is if you can maybe tell us about some of the biggest challenges that you had during your PhD and kind of all the projects that went along with that.
Yeah, it's a really good question. I think for someone like myself who's very excitable about science related topics, the biggest issue for me is balance and finding balance in the research process and remembering that I can't do everything. I cannot take on every project that comes my way, and there's plenty of science to go around. And as much as I want to work on everything and anything that relates to these paleoclimate questions that I'm interested in, I have to just kind of focus sometimes and maybe let go of those projects or maybe work in a more reduced capacity. I think that's been a learning experience for sure. It's finding that balance of focusing on one or two, maybe three projects at a time, but not letting it balloon into everything that piques my interest because that's just like never ending.
Yeah, that's fair. When I was doing my master's, it was like a combined, like our cohort, I guess, was combined with a bunch of masters and a bunch of PhD students. I was lucky enough to kind of get a feel for what the PhD research is like without having to go through, of course, 6 years plus of research. It's almost like the people who are most successful take on the most projects, but then also end up working more and more hours for everyone else's projects. And I don't really know if I have a moral of the story with that, but yeah, just impressed with everyone who was able to keep that excitement up for years on end and help out, pitch in every single project. It's pretty impressive stuff.
Yeah, it sounds like you totally witnessed what I'm talking about, which
Yes.
is, yeah, it's there's so much science, so much exciting stuff too. But yeah, we are human. We need to take care of ourselves. We need to go explore other things besides just work and science all the time, even if we want to do it all the time. So yeah, it is a balance. And I think it's certainly not unique to me. I see it in scientists all the time, but it is definitely something I'm constantly having to remind myself of.
Cool, cool. And then, yeah, so I guess kind of moving on from research topic itself. So next, it sounds like you're moving on to a job, or sorry, you've already started a job, the Woods Hole Oceanographic Institute, which is, in my opinion, one of the coolest places you could work in the country. So like, just like super impressed and complimentary of that, I guess, to start off with. Yeah, I guess can you maybe tell us a little bit about what that's like, maybe some of your favorite parts of working there so far?
Yeah, no, I'm so excited. I really, it is the dream job. I would say, like, I'm very excited to be there. I've only been there for about a month now, so I can't really speak to any of the routines or anything that have been quite established there. But I think the coolest part so far has just been being surrounded by so many incredible scientists and minds, and they're also just so like nice and willing to have science conversations, and science conversations are one of my favorite things. So it is just great to talk with them and really come up with new ideas and brainstorm. So I think the people have been just the best part so far, and I'm really looking forward to more of that moving forward.
Cool. Cool. That's a great answer. I'll take it. And then, so something we were talking about for a couple minutes before we started recording here, we were kind of looking at, I guess I was asking you kind of, what do you want to see when you're looking for stars in the next generation? What do you want to see people get most excited about and get kind of devote most of their time to in the early stages of their academic or research careers?
Yeah, I guess so. The word stars, I guess, refers to the people who kind of like stand out, right? The people who you would like want to like that you're, let's say, in a classroom and you're like, oh yeah, like that's the person I want to be in my lab group or something. I think like at a place like Boston College, right? Like you were an undergraduate there, and everyone's just so smart and so capable and so excited about research. And I'm like, yeah, like let's like I want everyone to come work in the lab and come help out. And I think everyone would do an awesome job. So I think it's really rooted in the enthusiasm and curiosity aspect. And if you have those, then like I think you can go pretty far in science research. But I think the real limitation is that we have barriers in place to keep a lot of people from participating in science and scientific research that I think need to kind of be reassessed and deconstructed to make scientific research more accessible and equitable. So I think this podcast is an awesome way that you're kind of opening up the doors and making the science more accessible. But I think it goes from several different angles, and I think the stars will naturally kind of come out as people are able to get resources and learn about the science and become curious, because I think just as kids we're all inherently very curious and gravitate towards asking, but that really needs to be fostered and kind of cultivated throughout everyone's life. And yeah, the earlier on you can get earth science and paleoclimate into people's worlds, I think the better. And yeah, the stars will kind of come out naturally that way.
I think it's a really good way of putting it, and I totally on board with as much exposure to earth and environmental sciences, and really all sciences, but especially earth and environmental, as early as possible. For people who are maybe starting out their research careers, how would you recommend starting to get into this? Are you a fan of people kind of reaching out to professors or graduate students, or kind of starting their own projects? Where do you fall on that scale?
Yeah, I feel like this is part of the issue. I don't know if I like what the best answer is. I don't think it hurts to try emailing someone. The way I got in touch with Jeremy, for instance, is I was doing a little Google Scholar rabbit hole search and I came across his work and I said, I'm going to email him and see if he wants a grad student. And sure enough, it worked out. So a cold email never hurts. And the worst thing that could happen is they don't reply, right? Like that's not no answer. Like that's okay. So I don't think that hurts. I think yeah, seeking out opportunities where possible. But I think part of it is just like this accessibility thing of like, how do you integrate these topics into like kind of the classroom and kind of connect with like maybe museums and things like that. So I think this is kind of this is the challenge, but it depends how niche you want to get. If you want to learn more and get involved with specific paleoclimate research questions, go ahead, email the grad students, the professors, stop by in your department and just like pop in and see if they want to hire someone. Or in my case, I was just like, I'll do it for free and I'll just volunteer in your lab. And that is one way to do it too. But I think just being persistent in trying to find opportunities, and they will eventually kind of make their way to you, hopefully. But I know that not everyone has the same opportunities and access. So I think it's a tough question to answer.
Sure. And then what about classes to start off with? Do you think there's kind of a big difference with any of the classes to focus on undergraduate, any majors, minors, anything like that?
Yeah, I mean, your podcast kind of touches on the class that everyone refers to, like intro geology, rocks for jocks. Like, I think for me at least, that was my gateway into like earth science and earth science related kind of interests as I took the class and found it very intuitive and fun. And then from there, I just started taking more classes. So always, though people kind of like hate on it sometimes, they're like, "Oh yeah, like rocks for dogs. We don't need." No, I think it's great. Go take the intro geology class and see how you like it, and hopefully you have an engaging professor. But even if you don't like the first intro class, I'd say take another one because sometimes it can be pretty professor dependent or just like the mood of the semester. I think that would be my biggest piece of advice: is don't always rule it out after the first go.
That's a good point. Yeah, I'll say the earth science department at both schools I've been to, and probably everywhere, just like every other department, has some handful of professors that have tenure and are just, at some point riding it out. And totally fair. I get where they're coming from. But yeah, as you said, take a second class, get more perspectives, learn as much as you can, soak it up like a sponge. And then last question, kind of a fun one here. I know you said you're working a dream job right now. So if you don't want to answer this, totally fair. Do you see any kind of alternative career paths that you may have gone down if your life had gone slightly differently? I've had people talk about being coaches for different sports teams or, opening a surf shop, things like that. So yeah, anything else like that I'm open to.
Yeah, I love this question because I have a lot of varied interests outside of science too. And I've actually, as I mentioned earlier, dabbled in alternative lives and careers a little bit already. Like while in undergrad, I was pretty convinced I would work in a running store forever. I had a job working at a running store and I just absolutely loved it. It was so much fun. But then my passion for earth sciences kind of won out. And now running is just a hobby. Still love it. But I do still dream sometimes about opening like a bike and ski shop in a cute little coffee shop or bakery attached to it somewhere in Vermont or New Hampshire. And we live a lot of lives in our long life here, and maybe I'll still do it. Who knows? But yeah, I'd say that just kind of seems like it'd be a fun thing to do.
That's awesome. No, that's a great answer. Yeah, coffee shop, bookstore is my go-to in about, I don't know, 40 years down the line. So I think it's a great answer. Anything else you want to share with the listeners before I stop the recording?
Yeah, I hope that everyone learned something new. Feel free to reach out if you have any questions or if you're interested at all in like paleoclimate. Always happy to chat or direct you to someone who might have a better expertise in things. But yeah, I guess thanks again for having me on. And I think this is a really great thing that you're doing, and hope they helps people learn a little bit more about Earth and all it has to offer.
Perfect. Thank you so much, Danielle. I'm going to pause the recording here.